Okay, so we are going to start the design of columns, so chapter 10. And this also matches your ACI code. ACI code columns is 10. But remember, this is kind of the basic guidance for columns. You still have to combine these with chapter 22, which is your formulas. You have chapter 25 that gives you some detailing. And in this case, you also have chapter 6, which tells you some methods to simplify the analysis of columns. Okay? And so it goes with all these different chapters. But the basic needs, basic requirements for chapter 10 are here. But notice here it references chapter 14, chapter 19, chapter 20, because your steel, right? So it references different types of chapters depending on what you need. Okay, so let's start with that. Start with the basics here. So chapter 10. And of course, columns, I mean, we normally, when we see columns, we talk about compression loads, right? But columns could have tension loads and it could have bending moments, and therefore they are really beam columns. I mean, they behave like beam columns because you have moments, you have shears, you have axial loads. Okay? And so beam columns is much better because it encompasses or covers, I guess, all those different effects that loads can have on a member. Okay? Now, in most cases, we will have, in the case of casting place structures, it looks like a frame like this, very similar to your project, right? So lots of columns. And these are all fixed connections. I mean, the connections here at the end are continuous connections, right? And because of that continuity, then you definitely develop moments, negative moments, right, at the connections. And so you're going to have that, and the frames are indeterminate, okay? And the fact that they're indeterminate makes the analysis a bit more complex, right? Lateral loads, in this case, can be carried by columns, but in most cases, I mean, you will need some kind of a shear wall. We haven't talked about it as kind of an advanced concept with advanced concrete. I guess you talk about that. But it's the wall, reinforced concrete wall, that will carry lateral loads. Okay. Now, of course, you're using this RAM software, and there is SAP 2000, and there is Stat Pro, and there is RISA. I mean, you had different software packages. But before the software, I mean, we had to do that by hand. Okay? Analyze all that structure, doing all those low combinations that now you're doing by the software. All that done by hand. Okay? And of course, this guy, Hardy Cross, developed a method, the moment distribution method, that help, I mean, do some of that analysis. You have seen, I mean, the moment distribution in your analysis class. And it's good. I mean, it's a good method. It gives you, if you really work at it, it gives you very good understanding of how moments distribute, and what is the effect of the stiffness of a member in a moment. So it's done properly. You learn a lot out of that method. If you just did the calculations, then you just did calculations, so you didn't learn much except just to use the method. But nowadays, I mean, that method is no longer used except for very small analysis of structure, maybe a 2-member or 3-member at the most structure, probably for an FE exam or an SE exam or one structural exam, some kind of that. You may use it for that purpose, since you will not have a software available to do a complete analysis. Okay? But nowadays, I mean, everything is done on the computers, and we had to depend on computers, and you had to learn how to use these computers and understand what the computers are doing for you, and what is the answer that you are getting. Okay? as I talked about computers at the beginning, remember, you set up your structure and your structure is stable, the software will give you an answer. Mm-hmm. But it doesn't mean that is the correct answer. So you have to be careful with that. All right, so columns are going to be then designed pretty much like a beam. You follow the same principles. So that means you're going to have an A value to find your compression block, remember, right? Where you find your compression forces. So all that is exactly the same. That doesn't change. Okay, so chapter 5, whatever we learn in chapter 5 with using the compression block remains the same. All right. Okay, so you can see here an example of a beam column connection. The rebars go through, right? So you develop all these connections for continuity purposes, right? This one right here is a column that is being pushed by this element here, is being pushed laterally. So you're creating a bending of the column, right? And so columns can carry moments like that. And here's just the original development of the block, the A value and how it was. I mean, you may learn this in more detail. You take concrete behavior with Dr. Matamoros. He will go in more detail about the background of these formulas. Okay. So what are the types of columns that we have? Well, we have, in general, the columns can be square, circular, rectangular, cruciform, L-shape, T-shape, really, I mean, any form, okay? So any polygon could be a column. Okay? So, but the real categories are here. It can be tie columns, which means that you have ties, which are these horizontal members that you see here, right, as a certain distance, right, like the stirrups, right? But with columns, we call them ties. All right. Now, why do we bend the bars here? Again, to have the overlap with maybe a beam or something, right? So to provide the continuity, right? But this is a cage for a column, and you can see the ties. Okay? So that's what makes then a tied column. Now, if it's a circular column, you may have circular ties, right? Now, a spiral column is one that, of course, is reinforced by a spiral, like this, right? But a spiral requires, I mean, very, very specific spacing. I was going to see later, okay? And so we will see that. And then, of course, there are composite columns, and these are either structural shapes that are being encased in concrete. Okay? You can have an I shape, and you would put concrete around it, or you can have a steel that has concrete inside, like you can have a tube-type steel member, and you put concrete inside it. Okay? So those are possible type of columns. We are definitely not going to talk about this. Composite columns are mostly treated by the AISC. Okay, so the steel manual does pretty much composite columns. Okay? We're going to talk about mostly tie columns and a little bit of spiral columns. All right, so concentrically loaded columns, we've done this already, the short columns, right? We develop all these equations. These are the equations that we developed in chapter 5. This is your maximum load, ideal load, right? That you can develop in a member. We don't use that. Remember, we use 80%. If we're using a tie column, or we use 85%, if you use a spiral column, right? And that becomes then your N maximum for these cases. The N maximum in this case is for the moment equals 0. Okay, so this is the overall maximum load that you can put in a column when moment equals 0. So we did this practice before in chapter 5, so you don't confuse that for every moment that you have, there is a maximum value. So this value corresponds to the moment equals 0. If your moment is different than 0, then this is not your maximum. Okay? Could be, but it's not. Not necessarily. Okay? It depends how far you are in your eccentricity. Because the purpose of these 80 and 85 is to account for an accidental eccentricity that may reduce your capacity in your columns. Okay? And so that's why we have that percentage used for your M maximum. Okay. All right. So we have defined already all these terms. Don't forget that AST refers to the total area of the concrete section, not the tension side. It's total area. Okay. We also learned that in order to do this, we need interaction diagrams, right? And we can develop that, right? And I show you how to find a basic interaction diagram by just picking up point 1, point 1A, your balance condition, right? And then your P equals 0. Mm-hmm. So by doing those points, you can have an approximate value of your interaction diagram, right? Notice that you are a tight column, your eccentricity, the chopped off point here, which is your P sub n maximum, corresponds to a value of 0.10 of E over H. Okay? So your eccentricity is 10% of H. And so any point that is within that eccentricity, 0 to 10%, will give you the same maximum. After that, your maximum axial loads start changing with the moments. Okay. For the spiral is 5%. Okay. So that's what the limits are in terms of deciding the 0.80 and the 0.85. Okay. And so we went through all these different points. Remember that at some point, your phi factor, right, it starts being 0.9. There is your factor is a transition, right, and then your factor is a 0.65, right. So you remember those strength reduction factors will change depending on where you are in your interaction diagram, right. So we've done already all that. We talked about some of these already too. Your longitudinal reinforcement has a minimum 1% and a maximum 8%, right? You can write this in terms of rho g, no rho, but rho g, meaning that you're going to use area of steel divided by the gross area of your column, not the BD. So that's the difference between rho and rho g. Okay, so you're using here the gross area of your column. So you do that, you can write it in terms of that too, right? So you can use then the reinforcement ratio, or you can use the area, so on. Now typically we don't go past 4%, we don't get to this 8, and the reason for that is because you have to count those places where you put splices. So in splices, you normally kind of double up things, right? So that means that you can only go to 4% because you double, you get to 8%. Yeah? But typically, columns are going to have percentages less than 2%. Most are going to be 1%. Okay? What else do we need? We also talk about this. You have triangular ties. You can have triangular ties. You have a triangular column, right? You have to have 3 bars. Other cases, rectangular, square, circular, you will have 4. So, and you have actually spiral reinforced concrete, you need to have 6 to make it really circular, true circular, right? For a true circular, you want to have 6. Clear spacing requirements, we went through these too. The bars need to have a clear spacing of either 1.5, the diameter of the longitudinal bars, 1.5 inches, or 4/3 the diameter of the aggregate. Whichever is the value, it has to be greater than the largest of these 3. Okay? So you pick the largest value, that will be your clear distance that you need to have. These values, these first two values, are 50% more than what is required for beams. This one is the same. In beams was 1 times the diameter and 1 inch. Okay. All right, transverse reinforcement. This is important for columns. You're going to have transverse reinforcement. Okay. And the reason for that is simply that you have these vertical bars and you have compression on those bars. They will tend to buckle, right? And they can push the concrete and expel the concrete. And so you have to keep it in place, and the way to keep it in place is through the ties. So you need some reinforcement. It could be tie reinforcement or it could be spiral reinforcement, okay? Then if in addition to these requirements, just to keep the bars in place, you have to design for shear, that is shear due to loads or torsion, then you had to go to those chapters. I mean, you had to do the design according to those chapters, okay? So these requirements that are coming here are simply requirements that are prescribed, right, to maintain the bars in place for most typical cases. So you're using number 3 stirrups, right? Then your bar size is limited to number 10 or smaller. If you go to number 11 bars or larger, you have to use a number 4 stirrup. Notice that this requirement is the same requirement that we use in beams with compression reinforcement. Okay. All the bars should have these stirrups around. Okay. The spacing of the ties center to center must be not greater than 16 times the diameter of the longitudinal bars, 48 times the diameter of the ties, or the smallest column dimension. Okay, this gives you a maximum spacing, but remember, this spacing is for to control the lateral movement of your bars. It has nothing to do with the shear strength that you may need due to loads. Okay. The clear distance cannot be smaller than this. We already seen that, right? And every corner bar and every alternate bar must have a tie. Okay. No bar shall be further than 6 inches clear on either side from a lateral support. So what does it mean? Every corner, right, has to have that tie. You can skip one bar and you can go to the next one. That one has to have a tie. Okay? So only one bar can be skipped like that, and you can have a tie. In this case, for example, I had to put a tie here, right? There. Okay? Why? Because here my spacing went past 6 inches. So that requires a tie. So if this spacing, the clear spacing, is more than 6 inches, this one requires a tie. If not, I can leave it like it is and I go to the next one. The next one has to have a tie, no matter what the spacing is between the bars. Okay? So you can only skip one bar if your clear spacing is less or equal than 6 inches. If your spacing is greater than 6 inches, you cannot skip any bars. Every bar has to have a tie. Okay? Very important. Okay? Other requirements are shown here. For example, you find your spacing for your stirrups here, where your tie is normally here. Then this one right here, the first one from the top of your floor, is at half of the spacing that you got here. The one here below the bar has to be at 3 inches. Okay, that's a special requirement. You may need extra ties here because you are bending the bars, and so to keep it in place, you may need extra bars. So you have to look at that too. So those are extra things. Okay, the same here. This is S, then this will be S over 2. Just the first one above that there. Here, because this is a slab, not a beam, again, is below the bar. We're going to have S over 2 again. Okay, in there. Okay. So you have a gap here between this one and the other member, which is that the column more than 3 inches, then this bar should not be bent. You will have to put a dowel bar to kind of splice here and transfer the loads. Okay? So those are kind of details. So that's part of the detailing of the concrete. Okay, we don't calculate those things. We just put them there, basically. Okay, other thing that we have here for a circular tie, right? We need to have an overlap of 6 inches. Right? So you have to overlap. There's an overlap here of 6 inches minimum, and the hooks here had to be standard hooks, meaning that 135 degrees basically. Okay, in there. Also, as you put these over these laps, right? If this is one tie, the next one above or below cannot be lapped at the same location. You have to lap it maybe here, or maybe here, okay? Or maybe here, halfway, right? But you cannot lap all the ties at the same location as you go up or down, all right? So you have to kind of stagger. So most people, what they do is they put the lap here for one, they put the lap here for the other one, then they go back to this one, then they go back to that one, and so on, right? As you move up and put in your ties, okay? In there. And also at the end, when you get to the top, when you get to the top of the at the ends of the spiral, I don't know if this shows that. This one doesn't show here, but you had to go like right here. So you see kind of double, bars, right? You are required to do that kind of turn there, okay? Right at the ends, you had to do like going around it, okay? So that's for the spirals. You do spirals, okay? So that's what that means by telling you here that anchor requirement, the end of the continuously wound bars or wires shall end a standard hook or have one additional turn, okay, completely turn. Okay. Okay. The design of the spiral reinforcement in columns. Why is that good, right? I mean, we use it a lot when you want a better ductility of the column. That will give you lots of better ductility, okay? So we use it for that purpose. If you're in a seismic area, you definitely want to consider that, because it gives you a lot of ductility, it protects you, it gives you more strength, right? And this is a nice background, but really what you're doing, this is kind of the idea of what you're doing, right? So you put the spiral, and then as you apply your load, this of course tries to expand, right? And then the spirals try to put them back into place, right? And so really the spirals are like putting like encasing the concrete, right? That's the idea. So that way the concrete will not spoil off at the inside, at the core. Okay? At the outside of the spirals, it will spoil off, but not inside the spirals. Okay? Now, you don't want to go through all this unless you want to learn more about history and things like that. But this is important. Okay? Notice that if I don't put that spiral, I just use ties. This is my behavior. But if I put these spirals, I mean, look at my behavior. I mean, it got a lot better, right? Especially in terms of ductility. Okay, it got a lot better, right? And so this is your axial deformation in terms of strains, and this is your lateral. This is the Poisson effect, right? Your Poisson effect also does the same. Okay? So it's very good. Okay? So that's important to remember. Okay, so what is the effect of this spiral? It helps you increase your ductility, and does provide extra strength. Okay? It does provide extra strength. So notice you're going here from let's say the worst case, this one. You're going from 2,500 to almost 32. So there is some increase, right, in there. And so there is that. Okay, so again, you don't have to worry about this test. This is kind of they did all this test and all that. Nothing there. This is how it works, really. I mean, you have the hoop stresses. Remember when you did mechanics of solids, and you look at those hoop stresses, that's pretty much what this is. Okay? But again, that's not important now. You, as I said, you want to read it later, that would be fine. And this again, test, don't worry about that. You can skip all these pages, And let me see, let me go here. Notice that there are comments there yet. So let me remove the comments. No mark. Okay, so we will have no mark. Okay, so this, you can skip all this. So keep all that. So this is what happens really, okay? You put that spiral, the core, what is inside the spiral, will remain confined, okay? Like encased, right? And so when the loads get pretty high, the outer shell will spool off. Okay? That spools off. You lose that, but you don't lose your core. So that means your column remains in place, which is good, right? You don't want it to fail. And so that's the whole idea of this. Okay? All right. So we skip all that, and then we get into what the code really wants. So this is the design of a spiral in ACI chapter 25. So that one is not in chapter 10, right? But the requirements are in chapter 25. Now, why in chapter 25? Because in chapter 25 you got details. So this is more like a detail, right? So how you're going to space it, all that is detailing, all right? So in chapter 25 is where you are going to find this. So I don't have my, oh yeah, I'm already there. 25.7.3, right? And so this is kind of detailing, so it's a lot of this. We're going to see that in chapter 11, a lot of this. But for now, we need the columns, right? And so for the column right here, okay, they have very nice drawings. I need to learn how they did that. Here, okay, let's first, let me come back to this one. So this is then the spiral requirement. Okay, this is the formula. Okay, we need to satisfy this, and here is the spiral. Notice what I was telling you. There is the overlap, right? Right, the overlap, 6 inches overlap with the hook. But notice we put one on this side, the next one that goes up, we put it on the opposite side, and so on, right? So we stagger the hooks, one on one side, one on the other side. Remember? So this is what we talk about. So all these things that I talk about, the distances and the clear distances and all that, they're all here. The hooks, the 135 degree standard hooks, right? So we have to use those. So all that about detailing is here. And that put me back to this one again. So this is what I show you. If it's more than 6 inches, right? So you have to put the ties. It can be one tie like I show you. You can do this diamond thing, but you have to cover all this because you exceeded the 6 inches. If this is less than 6 inches, yeah, you're okay. You don't need a tie there. Okay? But if you exceed the 6 inches, you have to pick it up as it come with a new tie. So this is very common in this column, right? You can do that. These are the individual ones. You can do the individual ones like this. In there. Again, to skip this one means that this clear spacing is less or equal than 6, right? Now, instead of doing this, you can do a double tie like that, and then you have to do one here in the middle to cover the others, right? So you can do that too. So there are different ways of providing that. But what is the key thing to remember? If the clear spacing is less than 6 inches, you can skip one bar. The next one has to have some kind of tie. Okay? If it's more than 6 inches, you cannot skip the bar. It has to have a tie. All right. So I think those are the nice stirrups. Here is the 1.5 extra that I show you in the photo, right? You have to turn around to make sure that the ends of the spiral go at least 1.5 turn extra. Okay. So these are very nice drawings. I mean, I wonder what software they use for doing this. All right. Okay, so we do that. And so here's the formula. We're going to use that one. FYT, yes, it's called a YT because the spiral is a transverse reinforcement and is limited to 100,000. Okay. ACH is area of the core, okay, of the spiral reinforced column. And let me see. They have a good picture here. No. Oh, they don't. So probably the better picture would be this one. So the area of the core will be all the way outside to the exterior. Okay, all the way to the exterior. That is your area of the core. Okay. Okay. And then AG, of course, is the area of the whole cross section, right? And F prime C, you know. Okay. So that's where you need to satisfy it. And that we're going to use this formula later. Right now, I don't think we have an example yet. Okay. Also, the clear spacing shall not be less than 1 inch or 1/3 the aggregate. But no more, look at this, but no more than 3 inches. What spacing are they talking about? This one. The vertical distance between this turn and the next turn, right? Cannot exceed 3 inches. That's it, 3 inches. That's all you got. Okay? And it cannot be lower than 1 inch or 4/3 the aggregate because you want to make sure your aggregate flows through, right? But so you're looking at 1 inch to 3 inches. That's it, right here. Okay? Very close to spaced, very close. So that's what I say. You're pretty much you're encasing the concrete with these bars. Okay? All right. Spirals need to have a diameter of at least 3/8 in casting place construction. Okay? At least 3/8. All right. So that's for now. Okay, we are going to use the formula, but later, not now. Cross-sectional dimensions. The code does not give you really a minimum dimension for a column. Why? Because you can have, small columns for maybe a storage area, some sheds, right? Some light construction in the house. And so for that purpose, they don't give you a minimum. You can use whatever you want as long as you make it work. Designers normally recommend 10 inches for rectangular columns, 12 inches for circular columns. Okay? And one thing to, if it's possible, one thing to keep is that the ratio of the long dimension to short dimension, when you have the rectangular columns, shall not exceed 3. Otherwise, it kind of becoming like a wall, right? It's no longer a column, it's looking more like a wall. And so that's why. Okay, that's the only reason for that. Now, when you select your dimensions, you have to consider slenderness effects. What is this? This is what you learn in mechanics of solids. Mechanics solids, right? Buckling, columns, compression members, right? Buckling. Okay? So we're looking at this. Okay? So we need to know that. So when you understand slender main members in concrete, the first thing you need to know is if it's braced or unbraced, right? And some of you have taken a steel design, and so you know what a braced member is in steel design. But in concrete, we don't have that kind of braces. What we have is walls, right? And walls act as braces. Mm-hmm. And so we have then brace or non-sway frames, right? Which is another name for braced, or swayed and inhibited. There's another word. I think that's the word they're using in the steel manual, right? Brace and non-sway frames, or sway and inhibited. Inhibited, and inhibited. Okay? So you have those. Okay. So that means that the displacement of this column, right, is going to be minimum, almost zero, right, because of this wall. Right? But how do you check these things? Okay. Method 1 in ACI 6643A. So now we're looking at section 6. See, that's what it said, analysis. Remember I told you that you had to look at the analysis, right? So in the analysis, we're going to go to this section. So notice here, some of you may be looking at this. Oh, I've seen that before. Okay, so 6643 is coming here. So you have here 6643. So you shall be permitted to analyze columns and stories as non-sway if A or B are being satisfied. So what is A or B? A is this one, the increase in column end moments due to secondary order effects does not exceed 5% of the first order end moments. Oh, okay. Or you use this Q method, which is really described later, right here. So those are the two methods given there. So let me now move this one up. And that's what I'm saying here, okay? So second order analysis results are less or equal than 5%, 1.05 from the first order analysis. And then your Q method. Okay, so let's start with this one. Second order analysis. What is that? Remember what I was telling you? You may have an analysis, but I can tell you that your moments and shears and everything is wrong. Okay? Why? Because it depends on the analysis method you're using. You're using first order analysis, you get one answer. You're using second order analysis, you get a second answer. So what is the second order analysis? The second order analysis ideally will include the effect of the fact that when you apply your loads, if this member moves, then the loads are now moved, and therefore they create a displacement, and that displacement creates an additional moment. Okay, so that's kind of the geometric effect. You may also want to include the non-linearity of the material. That would be great. You can include all that. You want to include creep effect, right? So all those things can be included. So there are different levels of second order analysis depending on the complexity of the problem, right? The more complex ones, they have all this geometry, you have your non-linearity, you have your creep, your shrinkage effects, and all that usually are at the level of research, they're more at the university level. The commercial ones do not have as much. Some may do have a little bit. But they offer second order analysis, and they definitely give you the displacement effect. Okay, but that's another level of analysis. Okay? So there are different levels then of analysis depending on what you're trying to do. Okay? So we have to do then that we run it for this one. We use this method. We run it. Then we look for a software that offers this option. Then we run it again, right? And we compare the results. And if we get this 5%, we pass the 5% difference, then we got a case that now sways rather than non-sway. Okay. Method 2 is using this, which is called the stability index, or simply the Q index method. Okay. In this method, it's more like a hand calculation method that you can use. Okay, so what that means is you're going to do this analysis, okay? And then you use these values, the first order analysis, and you're going to put them here and check them. Okay, so you're going to have then the summation of the loads on a given story, the shear on a given story, the length of the column on that story, and this one, delta zero, very important. The relative, okay? Not like your parent, no, the relative lateral deflection, okay? So this is relative with respect to the different floors. Okay? And I have made, I think, a copy for you here someplace for that purpose. Okay? So you're going to get, you apply your forces, you get your displacements, delta 3, delta 2, delta 1. Right? The relative value is the difference between delta 3 and delta 2. That's the relative displacement for the story number 3. Okay. The relative displacement for story number 2 is, of course, delta 2 minus delta 1. Okay. the relative displacement for the first story is simply delta 1 minus 0, because this is your support, right? So you get that one. What is your shear for a story number 3? Well, you make a cut here, right, before it, and your reaction has to match this force. So the reactions in your columns have to add to this number. That is your shear at that story. You look for the second story, you make a cut right before it. Again, the reaction on these columns have to add to these two forces. So now you got your shear on that story. When you do here, you find your horizontal reactions. Those had to be equal to these three forces, right? So you have your shear on the first story. So you can see then you have different deltas for each story, different shears for each story. So you have to check each story. Okay? So you have a building that is 10-story high. Well, you have to do this calculation here 10 times, all right, for each story. Okay? Because one story may be okay, the other story may not be okay. Okay? All right. Now, of course, you can always simplify, right? You may look for the worst cases and see that one passes, then the other ones are not going to pass, right? You can always do things like that to simplify. But in principle, you have to check every story. Okay? And that tells you what these are. LC is, of course, your length of the column, right? Center to center. Okay? So this goes to the joints. Okay? Center to center. Okay? Now, when you find that value for each story, right? And the value is less or equal than 5%, then you're okay. The frame is braced. Otherwise, the frame is unbraced. And the last method that we have for that one is in section 625 of your code. And so that one will be so 625 is here. See if I got that right. Maybe I have this wrong. I thought no, right here. Yeah, right there. There it is. There it is. There it is. Okay. If bracing elements resisting lateral movement of a story have a total stiffness of at least 12 times the gross lateral stiffness of the columns in the direction considered, then you can assume that the structure is braced. So what are they saying? So for that one, I think I did here another drawing for you. Okay. So these are my excellent drawings, right? So here you have little column 16 by 16, another column 16 by 16, another column 16 by 16, and then your wall, right? So you're looking at the cross sections on and giving a story. Okay? So column, 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 and wall. So what they're saying is, okay, so this is the member that is bracing everything. So you're going to find the stiffness of this member. So you're applying your wind in this direction. So your columns are going here, up, 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 your wall too, right? And you're bending along this axis, right? So that means that your H is 10 feet for the column. So you have to change that to inches, right? Your width of the column or the wall here is 10 inches. You find your moment of inertia. So this is the moment of inertia of the wall. Each of the columns, well, they're squares, so in this case, then you're always in 16 all the time. But this is important. The axis, remember we talked about this. The axis of bending is important because if it's rectangular, right, the two dimensions are not the same, so you need to know which one to use. Okay? And so the dimension should always parallel to the direction of your lateral loads. That's your H. Your H is always parallel to the direction of your lateral load. Okay? So your H is 16, 16, 16, and 10 feet. Okay? All right. So assuming that you have the same material, the lengths are the same, which typical are for one story, right? They're going to be the same length. you got the same material, then your stiffness depends only on the I value. And you may have remembered this, I don't know if you were told that, but you should remember from actually doing that Hardy cross. Remember your cross moment distribution method, right? When you did your moment distribution method, you have this 4EI over L, right? But you didn't use all that. All you used was the I and the L, right? Because your beams have different spans, so the L has to be considered. But the E, which is your material, right? Your modulus of elasticity, you ignore it, right? You simply use I over L. If the L's were the same, you only need to use the I's, okay? In the case of the columns, because you're looking at the stories, right? A typical story will have, right? A typical story has the same column, right? The same heights. So the length is the same. So you can ignore then the length, right? And all you have then is the I left out of that stiffness value. So if we look then at the I of the wall divided by the number of columns that you have, so notice that the value is 117. That's a lot bigger than 12. So the columns are braced. So a 10-foot wall will brace this column no problem, right? It can go to even 9 columns and still will brace them okay. So that's what they mean by that 12. So the wall stiffness has to be at least 12 times the stiffness of all the columns it's trying to support. Okay? So that's the concept of this one right here. An unbraced frame, of course, is one that doesn't have bracing, and it will depend on the individual members, your columns and girders, to support the lateral movement. Right? So let's look at this, for example. Here is a frame. Okay. It has lateral loads, it has your vertical loads, and this is something that you will need to do for your frames, right? You will have to do this after you do the analysis. You are going to collect these values, which are your deltas, right? Your displacements. You're going to collect your reactions, right? And you're going to find your Q values, because you need to decide if your columns are going to be braced or unbraced. Right? And so we have all these loads, and we do a linear elastic analysis. So this is just a regular first order analysis. And you find the displacement of the joints C, joint F, joint I, joint L. You get your displacements. Then you find the displacements at the other level, right? So that's your B, your E, H, and K. You find the horizontal reactions, H, negative 2.2, 7, 8, 3.3, 11, right? And then you have your vertical reactions, right, in there. Okay. So we're going to then find the Q value. Now, because our displacements are not exactly the same, and they are not the same simply because when you use one of these structural software methods, right, they consider the effect of the axial stiffness, and that will create a little bit of difference in your displacements. Okay? So they are almost the same value pretty much, but they're not exactly the same. If you ignore the axial stiffness, you get only one displacement, one value for all the joints. So that's why they do. So we're going to find an average. So we're finding average of the displacement. That's what you got on the roof. And then at the second floor, this is your average. Now we need to do the relative value, right? So the relative value at the roof will be this value minus this one. So that's 0.12. The relative value for the second floor will be this number minus 0, because it goes to the support. So that's 0.36. Okay. The summation of axial loads, right, in the second story. So that means, what is the axial loads that you got here? And you will say, well, you didn't give me that. No, you know your load here, right? That's 3. The forces in your columns, right, have to add to this load. You cannot have more than this load. So if this is 3, then you have to multiply 3 times 30 plus 24 plus 30, so times 84. That's the total load that you got here. Therefore, the reactions on your columns have to be equal to that value. Okay? No matter what you do, which way you put it, how you cut the frame, how you do it, you can twist it, you can push it around, you can do whatever you want. The summation of the loads, vertical loads, had to equal to this number times the length. Okay? And so that's what it is. You got it? Okay? This is your value. Okay? What is the value for these ones? Oh, now I need to add this load and I need to add this load. Right? So I do the same. I can do 3 plus that 7.8 times the 84. That should be my axial load. Now, in this case, I also gave you the reactions. So the reactions will be the same thing. You add the reactions, that should add to the total load, right? And so I did it both cases. I did that one. This is the first one we already found. Now we do this, the second floor. This is my value. Or if I add my reactions, right, I get the same answer. So that's for your first floor. Your shear on the second story. Remember, you make a cut right before it. The summation of the horizontal forces on your columns had to equal 12. They have to be in equilibrium. Okay? So that's 12. The summation of the horizontal forces here had to be equal to 20. Okay? Or you can use the horizontal reactions to find the same value. So I did that. My top story 12, the other one will be 12 plus 8, 20. Or you use the reactions, you get 22. Okay? So they have to match. Now that I have the values, I find my Q value for the second story. So my forces, my relative displacement, my shear, the length of the column, change it to inches, and is 0.017, is less than 0.05. The column is braced. So the top columns are braced. Okay. I do the first story, and I got my forces, my displacement, my horizontal shear, my length of the column, and now this is higher than that. My bottom columns are unbraced. Okay? So in a building, you can have braced and unbraced columns depending on how they're being set up. Okay? And so that is this calculation for this purpose. Next class, next presentation, we're going to do this slender. So right now, all you have learned here is some details about columns. We review the formulas for your P naught and your P sub n maximum. We mentioned the interaction diagram, which we need to use it again. And we have learned how to check for being braced or unbraced. Okay?